So we're continuing in section 9.1, talking about sequences. So again, a sequence, we have some kind of list of numbers. They have some kind of relationship to one another. We said that we define the sequence as a function whose domain is the positive integers. So just as a reminder, we're going to talk about a couple of theorems for convergence for sequences. So the first one is the squeeze theorem. And our squeeze theorem tells us that if we have three sequences, so we know that the limit as n approaches infinity of a sub n is some number L, and that also equals the limit as n approaches infinity of some other sequence b sub n. And if we have an integer n such that after we get to a certain term in our sequences, that our nth term in the A sequence is less than some other value, and it's also less than our nth term for our B sequence. So whenever we count out past this certain value of n, then the limit of our C sequence as n approaches infinity also equals L. So we know that the limit of the A sub n and B sub n are L, and if we have a third sequence that eventually is between the nth terms of each of these sequences, then the limit, I forgot my C here, the limit of the C sub n of the C sequence is also L. So the limit of the C sequence is just squeezed between the other two. And if we want to think about this graphically, just a quick sketch, if these are my axes, and we're going to say that these are the terms of A sub n, and I'll connect that with a little line here. So this is A sub n, and down here we have B sub n. And then draw my line through my points very well. So there's my B sub n series, and I just connected them with points just to make it easier to see. And my values for C bounce around in between here. So here's C, but eventually they fall inside here. So if I connect these with a So this is C sub n in the green. So if eventually C sub n is between the nth terms of the C of my C series is between the nth terms of A sub n and B sub n, then the limit of C sub n has to be L as well. The two series squeeze the limit down to L. So that's why we call it the squeeze theorem. And graphically, this is what it's telling us. Does that make sense? So, in essence, what this is saying is n becomes large. C sub n is between A sub n and B sub n. So that's one theorem that we can use to show convergence of sequences. Is if we can use this squeeze theorem, if we can put it between two other sequences. And I'm not going to go through. We're not going to go through a lot of proofs of theorems for convergence. We might look at a couple. Some of them get kind of long, and it's easy to get lost in the details and miss the big picture. So we're not going to prove a lot of these theorems. All right. Another theorem that we can use is the absolute value theorem. So this is a theorem that we can use to prove the convergence of a sequence. And what the absolute value theorem tells us is that we have a sequence A sub n. If the limit as n approaches infinity of the absolute value of the term is 0, then the limit as n approaches infinity of A sub n equals 0. So if the absolute value sequence converges to 0, the original sequence converges to 0 as well. So the absolute value theorem will help us show convergence to 0 if we need to show convergence to 0. And that makes, intuitively, that makes some sense, right? All right. The next idea that we're going to talk about is monotonic and bounded sequences. If any of you ever go on to take math beyond differential equations, you ever take an analysis course, or when I was in school it was called advanced calculus. These ideas of monotonic and bounded really play a big part. And we'll get to an idea as we're talking about these monotonic and bounded sequences that really plays a central role in what I talked about yesterday in making calculus rigorous. And we'll get to that in just a minute. So we're going to define monotonic. So a sequence A sub n is monotonic if its terms are non-decreasing or non-increasing. And what do you think we mean by non-decreasing or non-increasing? What's that? It could be constant. So let's look at non-increasing first. If we have a non-increasing sequence, what would that tell us about the sequence? Could be constant. We decided it could be constant, so it's not increasing if it's constant. What else would make it non-increasing? If it oscillates, so think about the terms. Think about the word non. We're talking about non-increasing. If we have one term down here and the next term up here, did it increase? Did the terms increase? Right? So non-increasing means that either it's constant or it is always decreasing. So non-increasing means well, non-increasing means it could be constant.
There are two different types of
A constant sequence is non-increasing.
But you just said it is or to decrease.
Oh, so there are two separate conditions. It can be non-increasing or it can be non-decreasing. Then we call them monotonic. So non-increasing means that a sub 1 is greater than or equal to a sub 2, greater than or equal to a sub 3, greater than or equal to ... greater than or equal to a sub n. So the terms, the value of the terms is either constant or it's going down with each term. And non-decreasing means that a sub 1 is less than or equal to a sub 2, less than or equal to a sub 3, less than or equal to ... less than or equal to a sub n. So it's non-decreasing, the terms are either constant or each one is greater than the previous one. So if either one of these conditions is true, our sequence is called monotonic. So it's either constant or it's going up with every term or going down with every term. So that's our definition for a monotonic sequence. Now we want to talk about what we mean by a bounded sequence. So does monotonic, are we clear with what we mean by monotonic? Okay. All right, so a bounded sequence. What we mean by bounded. A sequence is bounded above. We have three things that we're going to talk about. A sequence a sub n is bounded above if we have a real number we have a real number m such that our terms are less than or equal to m for all n. So that just means that we have some number that's bigger than greater than or equal to any term in our sequence. And we call m the upper bound. And similarly, our sequence is bounded below if there's some number that is less than the terms of our sequence for all n. So this real number n is less than or equal to all of our terms for all n. And we call n the lower bound. So bounded above, we have some number that our terms don't increase beyond. Bounded below, if we have some number that our terms don't decrease beyond. So our bounded sequence, the sequence is bounded if it has an upper and lower bound. So if we have some number up here that our sequences don't increase beyond, some number down here that our terms of our sequence don't decrease beyond, then our sequence is bounded. It has to be bounded above and bounded below to be called bounded. So we have a bounded sequence if it's bounded above and bounded below. Now we have to do a little hand waving here because there's a concept that we're going to that our theorem relies on that's really quite a bit beyond what we're doing. But there's an important property of the real numbers, meaning that they are complete. And by complete, it means there aren't any holes in the number line. There aren't any missing numbers in the number line. Between any two numbers, you can find another real number. So we don't have any holes and gaps. What that means is that if a sequence has an upper bound, then it has a least upper bound. And if you go further in math beyond differential equations, that idea of a least upper bound is going to play a huge part. So if we have an upper bound, then our sequence has the smallest upper bound. We can pick the smallest upper bound that's an upper bound. And it also has a greatest lower bound. So we can pick the largest lower bound, and we can be sure that greatest lower bound is unique. We can use these ideas to show that bounded monotonic sequences converge.
Does that mean that they're both bounded and monotonic? Or are they two, bounded converge and monotonic?
Both conditions have to be true. They have to be bounded and they have to be monotonic. So if a sequence is bounded and monotonic, then it converges. But it takes quite a bit of little more advanced math than we know right now to show that this is true. If A sub n is bounded and monotonic, then it converges. So if we have some sequence, if we can show that it doesn't increase beyond a certain number, if it doesn't decrease beyond a certain number, and it's monotonic, it's either non-decreasing or non-increasing, then we know it converges. We don't necessarily know what it converges to, but we can prove that it does converge. And if you think about a non-decreasing sequence, so the terms are getting bigger and bigger and bigger and bigger, constantly getting bigger, but there's an upper bound, it makes sense that that's going to converge. And the same if you have a non-increasing sequence, the terms are constantly getting smaller, 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 but they don't get below some lower bound, then intuitively that makes sense that's going to guarantee that your sequence converges.
So if it's decreasing, do you only have to prove that there's a lower bound, or do you have to prove that it's...
You have to prove, if you're going to say that it converges, you have to make some kind of argument that there's an upper bound.
Why?
Because the conditions of our theorem are that it has to be bounded up above and below. So if it's, you know, if your sequence starts at 1 and keeps getting smaller, you can say 1 is an upper bound. Just it never gets above 1, just because of the rule of the sequence or something like that. But you have to make some kind of argument saying it has an upper bound and a lower bound. Even though it seems it's obvious sometimes, but you do, in order to satisfy the theorem, you do have to say that. All right, so what I want us to do, these are the main ideas for the end of this. In our book, on page 603, I want to look at numbers 103 through 108 and talk about these a little bit. Yes.
Can a sequence be monotonic if it is like 1 over n or something like that? Is that still monotonic, or is that not monotonic because of stuff before n equals 0?
If you say that you're defining your sequence as 1 over n for n equals for the positive integers.
But isn't that inherent though if it's a sequence? Is that
Yeah,
all positive integers?
all positive integers. So 1 over n would be monotonic because it's constantly decreasing.
All right, so currently 4 minus 1 over n is monotonic, so according to the book. Could it be clarified that that's that drop down, or is it taking it in the non-positive integers?
Which problem are you looking at?
87 or 83.
On page
603.
603?
It's not in our homework, but I
Oh, okay.
figured I should look at it on
So let's see. We want to determine if it's monotonic. 4 minus 1 over n.
Yeah.
So
So I make sure that it does say that. I think I looked at 87 when I was looking at it in the answer section.
yeah, let's double check.
Oh yeah, 83 does say it's monotonic.
Okay, yeah, I was thinking. I would say it is monotonic. Okay, so let's look at pages on page 603. We want to look at 103 through, and 108 goes on to page 604. So let's talk. This is kind of a review, kind of a recap of what we've done. So how we want to define a sequence. How did we define the sequence? Who can give us a good definition? Doesn't have to be the technical definition, but how are we thinking about a sequence? So a function whose domain is the positive integers. It's just a collection of numbers where their relationship is this function, and we're plugging in for our domain values positive integers. So when we're talking about the convergence of a sequence, what do we mean when we say a sequence converges? So the values of the sequence get close to a point. We talked about the idea of a limit. So our terms of our sequence get closer and closer to this particular number. So that's really what we mean. When I think in everyday terms, when you're thinking of convergence, you're thinking it gets close to, and after a while, it just gets closer and closer and closer. Monotonic. How are we thinking about a monotonic sequence? Non-increasing, non-decreasing. Could be constant, or the terms are constantly increasing or constantly decreasing. That's what we mean by monotonic. Bounded. What do you mean by bounded? It has boundaries. It doesn't get bigger or smaller than something. So let's, number 104, this one should be easy. So you have two graphs there for number 104. Which one which terms have alternating signs? The first one, that one's easy, right? The next ones are a little trickier, number 105 through 108. So number 105 asks us, it says, gives an example, we want to give an example of a sequence satisfying the condition or explain why no such sequence exists, and examples are not unique. So what I want you guys to do for a little bit is work on 105 through 108, and then in a couple of minutes we'll talk about these. So before we start talking, I listed some limits that come up frequently that it would be good to know, or at least be familiar with a little bit. And this is the one we talked about when we talked about our homework. And for all these, x is fixed. So x is not varying. We're looking for at a specific x. So let's look at number 105. It says it wants a monotonically increasing sequence that converges to 10. Anybody have an example of that? Cool.
10 minus 1 over n.
10 minus 1 over n. That's the one I came up with also. So I think that one's the easiest one. 10 minus 1 over n is a monotonically increasing sequence that converges to 10. Numbers 106, a monotonically increasing bounded sequence that does not converge. What is it?
It doesn't work.
It doesn't work. It's impossible. A bounded monotonic sequence always converges. Number 107, a sequence that converges to 3/4. Someone other? Star? What's that? A sub n equals 3/4. There's an easy one. That sequence converges to 3/4. That's just a constant sequence. Did anyone come up with something more complicated? What did you come up with, Chris?
3/4 minus 1 over n.
3/4 minus 1 over n? Okay. Cole?
I did 3/4 n over n plus 1.
3/4 n over n plus 1. So if you're thinking of think of a rational function, if your power, if the degree of n in the numerator and denominator is the same, it's going to converge to the ratio of the leading coefficients. So you could think of it that way. How about number 108? Unbounded sequence that converges to 100. Unbounded sequence that converges to 100. Okay. What did you say something over here? Okay. Because so Garrett doesn't think it's possible. An unbounded sequence? Does an unbounded sequence converge? No. Unbounded sequence doesn't converge. So it's not possible. One other thing, I'll give you your homework. I just want to say one other thing. When you're working with bounded monotonic sequences, when you want to show that a sub n, for example, a sub n is less than or equal to n plus 1, I want you to get into the habit of making a stronger argument than something like, oh, this one is bottom heavy, so this happens. Think about making a little stronger algebraic argument than that. So you work with those inequalities. So if you're showing that, if you want to show that a sub n is less than or equal to a sub n plus 1, work with these inequalities to come up with an inequality that you know is that you can state is false, or a state that is true. So think about making a good, strong argument if you're going to use this idea. So our homework, page 603. There you go.